Hello everyone.
Hello, ma'am.
Hello. So how is the course going on? You could follow whatever the lectures we are doing.
Yes, ma'am, but some topics are find difficult. I think so. From my side, I am saying. I
Yes,
don't know
yes.
about others.
Mhm.
Maybe
Which
that it's too deep or
which
don't know
other
about.
topics you find difficult?
Mm. Nucleation process. I think
Okay,
so.
okay, okay. And
Mm. And not much, but that I found it's a difficult one.
yeah, actually, no, time is very less. You must have seen that this crystal growth, I took two lectures, whereas rest all is like finishing in one lecture. So it's itself very deep. So I am not getting that much of time. And there are like a lot of physics behind nucleation, which we could not cover. So maybe if you are more interested in that, or so you can just mail me and we can discuss. Okay.
And then what will be the type of question in Viva?
Viva will be covering this, like whatever there, na, you will be getting the notes also from. So whatever I have covered
Okay,
in the lecture, so it will be that only.
okay.
Basics, basically, I will be asking.
Basic. Okay,
Nothing beyond whatever I have taught you. Everything will be there.
okay.
So you can go through this presentation and all, and you can. And also, I will be giving. Today, I couldn't bring the assignments. So in my next class, so that will be on the 2nd of January. So I will be giving few assignments, and 50% of the marks will be on the assignments. So already we have got some four questions we already have done, and there will be few more assignments. Okay.
Okay. But ma'am, when we mail our questions, na, so we will get the reply. So for my two mail, I didn't get that reply. Yes, it is correct.
Oh, then it is on my fault. So I will see and let you
Okay,
know.
okay, okay.
Okay. So generally I try to reply everyone. It is correct or not. So okay, we will start today's lecture. So before going into that, today I will be covering the thermoelectric materials. This is the part we will be starting now. And before going into that, I will give the answer of the last two questions which I asked last time. One question was what is the similarity between homogeneous and heterogeneous nucleation and heteroepitaxy and homoepitaxy. So all of you have answered it correctly. Yes, like in homogeneous nucleation, it is the growth of same kind of seed is there and the material, same material is being grown. Similarly, in homoepitaxy, the film and the substrate both are same. So in that way, and in heteroepitaxy, the material, the film which we are growing and the substrate, they are different and having some crystallographic correlation. And similarly, in case of heteronucleation, also the nucleation of the crystal starts on a foreign body, which is not that material. So in this way, they both are very similar process. And my second question was on the deposition of SiO2, like why you will be choosing sputtering for SiO2 and not thermal evaporation. So the main, I think most of you have answered it correctly. One or two, there was some mistake or some confusion was there. So basically, for SiO2, we take sputtering because the melting point of SiO2 is very high, and that's why thermal evaporation is not possible, and also it can lead to disintegration of SiO2 at high temperature. And we will be using not DC sputtering but RF sputtering, SiO2 being a new insulating material. So if we use a DC sputtering, then there will be charge accumulation on the target, and because of which the sputtering rate will decrease. So we use a RF sputtering, and magnetron sputtering will always be beneficial because it will increase the sputtering rate. So our growth rate of the film will be higher. So the answer is for SiO2, we will be preferring to have a magnetron RF sputtering technique. Okay. And most of you have answered correctly. Even if I didn't got the time to reply each of you. I will mail it by today or tomorrow. And most of you have answered, but for the SiO2 deposition, I think there was one or two mail I could see that there was some confusion, but rest of you have got it properly. Okay. So now coming to today's lecture. So it is thermoelectric material. So these are so what is basically a thermoelectric material? Huh? So as the name suggests, uh, as the name suggests, thermoelectric material, thermoelectricity. So there are two words in this. We have got thermal and electricity. So traditionally, the term thermoelectric effect or thermoelectricity are are those materials which shows uh, we can generate electricity by using thermal means temperature. So before going into that, we see that how it has come into being. So it is encompasses three separate effects, which is the Seebeck effect, the Peltier effect, and the Thomson effect. Seebeck effect, most of you know that thermocouples, if you are using, so it is working on the Seebeck effect, and Peltier effect is the opposite of the Seebeck effect. So Peltier and Seebeck effect are most basic of the three and are essentially the inverse of one another, for which reason the thermoelectricity effect may also be called the Peltier-Seebeck effect. Now, like thermoelectricity is there, so we can think like when there is electricity flowing through any conductor, there will be some temperature generation, no? I square R. So that is the Joule heating. So Joule heating heat is generated when a voltage difference is applied across a resistive material. So it is somewhat related, but this is not the thermoelectric effect. So thermoelectric effect we will see are reversible. So similarly, the Peltier, Seebeck and Thomson effects are reversible, means we can change the direction or we can change it. Whereas Joule heating is not. So it is in a conductor when in the Joule heating, when in a conductor we are flowing the current, we get heating, but it is not a reversible process. Now we will be looking into all these three effects individually and see how thermoelectricity is connected. So starting with the Seebeck effect, what is the Seebeck effect? So a temperature across a material or a junction between two dissimilar material generates an electric voltage, EMF. So in you can see in this diagram, we have got this is one metal material and this is two material. And we have got junction 1 and this is junction 2. Junction 1 is the hot end, means it is at a high temperature, and junction 2 is the cold end, which is at a lower temperature. So what does it means that we have got, therefore in this two dissimilar material, there are two junctions and both the junctions are at a different temperature. So what happens, there will be an EMF. So there will be some voltage will be generated between these two. Okay. So this was discovered in 1821 and by Professor Seebeck, and it is generally the temperature difference generates a voltage. Now what is happening inside the material? You can see that we have one end as hot, another end as cold. So why the temperature generation is there? So in the material, because of the difference in temperature gradient, our carrier, charge carrier, maybe electrons. Generally, if we think in terms of metal, the electrons, so they will be, because of the temperature gradient, they will be flowing in one direction. So because the electrons, like they will be going in this direction, there will be some kinetic energy, directional kinetic energy. So the electrons will get accumulated at the low temperature and there will be less. So there will be a built-in potential. So between this, there will be an EMF. So because of that, we are getting the voltage. So the charge diffuses under a potential gradient of temperature and built-in potential which is resisting the diffusion. And this is generally defined as the Seebeck coefficient. S is the Seebeck coefficient and this is the difference between the voltage per unit temperature difference. So delta V by delta T. This is the voltage difference at the two ends and the temperature difference at the two ends of the material. And the working of a thermocouple. Thermocouple is a device which is used to measure the temperature whenever you are going to low temperature, high temperature, you are using a furnace. So you want to measure the temperature of anything. So like a thermometer, but in industrial, we are using thermocouples. And this is based on this Seebeck effect. Now coming to the Peltier effect. So what happens in the Peltier effect? This is like exactly the reverse. So in this case, flow of electric current creates cooling or heating effect at the junction, depending upon the direction of the current flow. So we have got here like iron and copper. And current is flowing in this direction, right? The current is flowing in this direction. So and there are two junctions, J1 and J2. So at one junction, depending on the direction of the current, heat is absorbed, and at the other end, the heat is evolved. So this becomes, when there is heat is absorbed, so the surrounding material at temperature decreases, and where the heat is evolved, it becomes hot and this end becomes cold. And the Peltier heat is defined as pi is the Peltier coefficient, and for each material, so the heat generator is the multiplication of the current flowing and the Peltier coefficient of the given material. Okay, so why it is happening? So it is essentially the reverse of the Seebeck effect. When a direct current is passing through a closed circuit made of two different materials. So we can take the materials as a metal also, but we can also take it as a P-type or a N-type semiconductor. So let us think that it is a P-type or N-type semiconductor, like bismuth telluride. So it forces the charge carriers like electrons and holes to move across the junction. At one junction, the charge carrier moved to a higher average energy state. What is happening now? You think about that our PN junction, which we have studied in the first class. So the electrons, because of the band structure of both the semiconductors, they will be at a different potential. So wherever it is good. So if the charge carrier is moving to a higher average energy state from a lower energy state, to make this energy transition, they must absorb thermal energy from the surrounding material. So we have got this kind of bands are there. So like electrons are there. And this is our junction. Or we have got holes are there. So if current is flowing from this direction to this direction, the two materials are there. So then what happens if electrons are the conducting and they have to go to higher potential? So they will taking the energy from its surrounding. So this makes this energy transition they must absorb the thermal energy or heat from the outside. So this causes the junction to become cool. So this becomes the cold side. And on the other, if the current is flowing from this direction to this direction, at the other junction, the charge carrier moves to a lower average energy state. They release their excess energy as heat to the surrounding. This causes the junction to become hot. And Peltier cooler, which are like very compact, small coolers, and we can achieve like minus 30, minus 40 degrees centigrade using them. So Peltier coolers are working on this principle. And now coming to the Thomson effect. So Thomson effect, this was predicted in 1851, and it says that any current carrying conductor, it is not a superconductor, it is a normal current carrying conductor, and this conductor has a temperature difference. So we have a current carrying conductor like this. There is a current here, and this is at temperature T1, temperature T2, between 2 points. So it will either absorb heat or emit heat, depending on the material. So what is exactly happening in the Thomson effect when both an electric current and a temperature gradient, both is existing? In the Seebeck coefficient, Seebeck effect, we were having a temperature difference. In the Peltier, we were flowing the current. But here both the electric current is also present and the temperature difference gradient is also existing. In a single conductor simultaneously, heat transfer occurs in the material in addition to the normal Joule heating. If one end is hot and the other end is cold, the charge carriers in the hot side have more kinetic energy. So we have got this, we have got T hot and we have got T cold. So this will be having more kinetic energy, so they will be moving in this direction. And if the current is in this direction, so now depending on what is our carrying majority charge carrier. So as the charge carriers move from the hot region to the cold region or vice versa depending on the material, they must either absorb or release heat energy, because if it is going from this direction to this direction, so it will be releasing heat. If the carriers, if the carriers are moving from this direction to this direction, so now it has to take heat from, because it has to go to the hot end. So they must either absorb or release heat energy to match the thermal energy of the new region. If the current flows down the temperature gradient from hot to cold, heat may be absorbed or released. If the current flows up the temperature gradient, the opposite occurs. So this is the Thomson effect. Now, how these three effects are now being used to understand the thermoelectric effect. So thermoelectric effect is the direct conversion of temperature difference to electric voltage. So very similar to Seebeck, you can say that in that case we were having two different junctions were there and we were getting an EMF. So this also thermoelectric effect is also very similar. Like we are directly converting the temperature difference to electric voltage. Simply put, a thermoelectric device creates a voltage when there is a different temperature on each end, and when a voltage is applied to it, it creates a temperature difference. This effect can be used to generate electricity. So that is why it is important. It is a energy harvesting material. It is a energy harvesting device. And it can be also used to measure the temperature or to cool objects, but this is the main advantage of a thermoelectric device. So it can generate electricity without using fossil fuel or any other thing. So you just have a heat source, and you are putting your material at a heat source, and then you have a cold end, and because of this temperature gradient you are able to generate electricity. So why the thermoelectric devices are important? We see that there are a lot of places where we are using the thermal energy. Like we have a thermal power plant, nuclear power plant are also there, automobiles are there, then waste incinerator factory. So here in everything we are using energy, primary energy. But if you see, only 34% of the energy is directly used, thermal energy. Rest is the lost waste heat. Even if you have an automobile, so if you see that lot of there is a waste heat on nuclear. So basically all the energy, it is very difficult to convert it. So this, if we can use this 66% of the waste heat, so it can be useful to convert it into energy. So here we can use a thermoelectric device, and this waste heat can be converted into electrical energy, which will be useful. So that is why thermoelectric devices are very important. And where it find uses, so if you see application of thermoelectric devices, it is everywhere. And how different devices are using which kind of heat. So if you see like body heat, so our body is also at a given heat. No? We are 37 degrees and is our temperature is there, body heat is there. So we can use this heat, and if we can make it is a, this is the hot junction, and our atmosphere or the room temperature is around 25 degrees. So there is a delta T. So this can be used to like running a wristwatch, or it can be used as a sensor for human presence or many things. Similarly, there is natural heat which are like we can we are not using it properly, like geothermal heat is there, then solar is obviously there, pavement heat or hydrothermal systems. So this heat can be like productively used. Then there is waste heat from vehicle coolants and exhaust gases. Your in your automobile there is a lot of exhaust coming out which is at a high temperature. So they are at a temperature of say 50 degree, 60 degree. So if we can use this heat, so it can be used to like even power your mobile or something like that. Then telecommunication, we are using low noise amplifier or devices are there. So they are also generating lot of heat. This can be used. And this electricity, if we are able to use this waste heat and generate into electricity, this electricity can itself be again used to cool those devices. So it is like a cycle and proper use, and there will be no wastage. Similarly, if we are talking about radioisotope heat, so there is a lot of decay heat when there is a radioisotope which is decaying. Like we can use strontium 90 or some sources are there. So this has been used for space probes. Like whenever there is a Voyager and all these space probes are there. So when we go beyond Earth, so the solar energy, because the sunlight decreases, so we cannot use solar energy to power them. So and this radioisotopes, they keep on decaying, and anything which has a half life of very high half life, so we can use these to generate electricity. So this decay heat of radioisotopes are used to now generate the electricity, and this can be like a remote, anything has gone remote but still it is producing electricity. So and even similar thing, any at a very remote place, like there is a desert or something, at those places also you can use them to generate the electricity. So lunar or Mars rover is there, and then industrial applications are so many things. So that's why these thermoelectric devices finding so many application, they are important to understand. And generally we are always emphasizing on the photovoltaics, no? Solar cells and all that. So that also we will be covering in our next lecture. But similar to that, thermoelectric devices to generate electricity are very important, and that's why it is important to understand them. So now coming to the thermoelectric devices. So what exactly a thermoelectric device is? So it is based on the Seebeck effect we have already learned. So it is a solid state device that converts heat directly into electricity. So it consists of a heat source. So we have got a heat source, so heat, and we have a cold junction. So it is, we will call it heat sink. So across this, we have a delta T. Now this delta T can be as small as say 10 degrees centigrade, or it can be as big as 500 degrees centigrade. So depending on that, depending of the kind of use we are and the kind of materials we are, so this delta T, and depending on the delta T, the voltage which we will be generating is depending on the temperature. So it consists of a heat source which is kept at high temperature and a heat sink which is maintained at a temperature less than the heat source. The temperature difference between heat source and heat sink causes direct current to flow through the load. So this thermoelectric generator is, so there is a load and we are getting some current here. Okay. So this is basically the working of a thermoelectric device. So by seeing into it, we feel it is very easy. No, we don't have to do anything. Just we take a thermoelectric device, a material, put it on a heat source, and then we will be, and there will be cold end. Cold end is always there, like there can be our normal atmosphere is there, and we can get the voltage. But when we see, it is not so easy. So before going into that, how this works. So if we have got just one material, it will not. So we, in this case, we use two semiconductors. We have a N-type semiconductor, we have a P-type semiconductor. In N-type semiconductor, we know the majority carriers are the electrons. So we have got negative, and in P-type, we have got the holes, and we have a hot surface and we have a cold surface. So because of this, we have electrons flowing and we have the holes flowing. Holes will be flowing from here, the electrons will be flowing for here. So what we get, we have, so electrons and holes will be flowing and we can have a electricity. So this is basically the working of a thermoelectric device. The output voltage and the output power are increased by either increasing the temperature difference between the hot end and the cold end, or by connecting several thermoelectric power generators in series. So if we have, this is only one module, this is one module. But if you think that there is one more module here, similar module we are keeping here. This is our N type, this is P type, then another N type, P type. And then we are putting it, we are connecting them like this. So our output voltage and power will increase. The voltage of this generator is given by V is equal to S delta T, where S is the Seebeck coefficient. So Seebeck coefficient of what? Our material, given material, and delta T is the temperature difference between both of this. So Seebeck coefficient and delta T gives the voltage of this generator at the temperature difference. All the thermoelectric power generators have the same basic configuration as shown in this figure. So their configuration remains same. So here I will see. So this is how a thermoelectric generator full will look like. So we have got a P type, N, a P, N. So you can see there are consecutively, they are connected to each other. And here you will see that this is the hot surface and this is the cold surface. Sorry. So they are thermally in parallel. Means in temperature wise, they are, all these are connected in parallel. Why in parallel? Because all at the top, everyone is hot and at the bottom, they are all cold. So thermally in parallel, but electrically in series. Because as I have shown in the earlier presentation, earlier slide, to increase the voltage, we have to connect them electrically in serial. So the current produced between this, so Pn, N to P, P to N. So like this current we have to do so that we can increase the voltage. And so this is now how it is there. So heat is absorbed on the hot side. We have got hole in the P type. In the N type, we have got electrons and they go, and then in the circuit, we get the electrical power. Okay. And here you can see this is like commercially available some thermoelectric generator. So this is like this is one end, this is another end, and just two electrical connections. So these are so EMF is between these two ends. And the top, the whole top will be say hot or cold, whatever. And similarly, this will be either cold or hot. Okay. So they will be like, as I said, thermally parallelly, all the modules will be parallel in temperature wise, and in electrical they will be series, they will be connected in series. Here also you can see a very one architecture in this like a pyramid kind of structure they have made, and in this like different modules are at different temperature. So like if we think that this is at say temperature, so this module is working at a different temperature, this module will be working at a different temperature. So we have a pyramid kind of thing, and ultimately we this will be the delta t, final delta t. But each module here inside is working at different temperature zones. So these are two of the architectures of a thermoelectric device. Now I will take just 1 minute break, and then we will come to see what are the materials which are a good gives good thermoelectric effect, and how they are selected. Okay.
And just a question.
Yeah, sure.
These thermoelectric materials have been used in the spacecrafts and satellites that are sent far away, right? Like the Voyager craft and all.
Yes.
Yeah, so in the cold of the space, the temperature difference would not be more than 3 or 2 Kelvin at best. So, and you said that these devices are used when temperature difference is about 10 Kelvin or so.
No, no, you are not understanding. The cold end is at your is the temperature of the surrounding of the deep space, but the hot end is being in contact, in thermal contact with this radioisotopes. So radioisotopes are, there is a decay heat when there is a radio decay. No, there is a decay scheme of say generally what are the radioisotopes used? They are either beta or the alpha particles. So because they are coming out with some kinetic energy and they are depositing their energy. So the hot end is around say 100 degree or 200 degree centigrade. So it is
So
not
the
like 2,
peak
3 Kelvin.
temperature is so much.
Okay, welcome. So I will take 1 minute gap and then we will come back. And if there is any question, just let me know. Okay. So till now, everything is clear. You could understand the Seebeck effect, the Thomson effect, and the Peltier effect, and how electricity is produced. So the point to understand is that the modules of the thermoelectric generator. So one end is left to the atmosphere. So that is at the atmosphere temperature, whatever is the ambient temperature. But the other end is heated or cooled. Hmm. So it can be heated. So that is where the waste heat. So like it can be an industrial waste heat or automobile heat. So it is like it is in close contact with, physically in contact with a heat source, a waste, basically with a waste heat source. So it is like if you are heating, say, water on a vessel. So some heat is given to the water which is getting boiled, but there is lot of heat which is being wasted, like your vessel is getting heated, so it is also hot. So if you can put your thermoelectric devices on the wall of your container and utilize that heat. So that is the essence of a thermoelectric device. Or if there is an industry is there, some boiler is there, so it is heating something. So there is a lot of waste heat which is being given to the atmosphere. This is not utilized. So thermoelectric device can be utilized to extract that waste heat. So that is the importance of this device. So like I was saying about the radioisotopes, which has gone to. So the radioisotopes are generating the heat, and so that is the hot end, and the cold end is what is at the ambient temperature. So it can be whatever is there, like in your room it can be 20 degree, or it can be outside like 25 or 30 degree, or it can be a cold desert which is at 10 degree at night. So there also you can use. So that is the beauty of these materials and this device. So now coming to is what is a good thermoelectric material. Okay. So a thermoelectric material is basically like quantified in terms of figure of merit given by Z, represented. So this Z represents the quality of performance of a thermoelectric material, how good it is a thermoelectric material, and it is multiplied with the temperature of operation. So it is called ZT. So ZT is given by, it is S is the Seebeck coefficient. So we have already learned that. And this is the conductivity, electrical conductivity divided by the thermal conductivity. So KE is the electronic part of thermal conductivity and L is the lattice part. So basically we see that ZT, the figure of merit of a thermoelectric material, it is directly proportional to the electrical conductivity and the Seebeck coefficient, and inversely proportional to the thermal conductivity. So to have it a good, should have high Seebeck effect and high electrical conductivity and low thermal conductivity. And for commercial purpose, for commercial application, we require Z greater than or equal, ZT greater than equal to 2. And but generally, whatever, if you see research going on and material which is, so around ZT of around 1.8 or so has been achieved and people are using it. But still to achieve a ZT of 2 is still a matter of research. Now, if we see how the Seebeck coefficient, what are the factors of the Seebeck coefficients are there, so that we can understand properly if we are into material research. So what material should I choose to make a thermoelectric device so that I can take out maximum power from a given temperature difference. So the Seebeck coefficient is given by S is equal to 8 pi square kb, our Boltzmann constant, and M star is the effective mass. So if you remember, again we go back to our lecture on semiconductors, where M star is the effective mass of the carriers, so of the holes or the electrons. So in a p type it will be the effective mass of the holes, in a n type it will be the effective mass of the electron. So directly proportional to the effective mass, and inversely also proportional to the electronic charge and the Planck's constant. And then we have got one more term here, N. N is the carrier concentration. So Seebeck coefficient is inversely proportional to the carrier concentration. So N is the carrier concentration. So we want to have a material which should have a bigger effective mass and low carrier concentration basically. So this rules out metals because metals will have high carrier concentration. Now coming to the electrical conductivity sigma part, so it is given by carrier concentration, charge, and mu is the mobility. So it should have good mobility, but the carrier concentration should not be very good. So, and then we come to the thermal conductivity. That was, we have seen that the ZT was inversely proportional to thermal conductivity. Now, if you see, we are requiring a material which should have very conflicting requirements. It should have very good thermal conductivity. Just a minute. कैमरा का डायरेक्शन Yes. I'm so sorry for this break. We were facing some technical problems. Um, so just what we were learning is that for a good thermoelectric material, we should have uh, so we should have a good ZT. A good ZT material, which is the figure of merit for a given thermoelectric material. So the ZT is dependent on the Seebeck coefficient, the electrical conductivity, and the thermal conductivity. So I was telling you that in a given material, you can realize that generally any material which has got good thermal conductivity also has good electrical conductivity, right? Like take the case of copper. So it has got both good thermal conductivity and good electrical conductivity. Or if you take an insulator, so it will be a bad conductor of heat as well as electricity. So, but here for the thermoelectric material, you want this relation, no, this inverse relation, that it should be a material which should be a good conductor of electricity, but a bad conductor of heat. Thermal conductivity has to be low. So we have to find that kind of material, and that is the challenge. That is the research in a thermoelectric material. If I am writing TE somewhere, it is for thermoelectric. Okay. So the Seebeck coefficient now in its dependent on the Boltzmann constant is there, Planck's constant, but mainly it is dependent on the M, the effective mass, and the number of charge carriers. And electrical conductivity is nothing but charge carrier, charge, and the mobility. So you want high mobility of the charge carriers, but the number of charge carriers has to be low. And now coming to the, if we look into the thermal conductivity of a given material. So the thermal conductivity has got two parts, the electronic part and the lattice part. So the thermal conductivity K is the property of a material which indicates its ability to conduct heat. The thermal energy can be transported by any type of excitation in a solid. And in our case, we are mainly interested in two types of contributors, which is the electrons and hole, means that is the electronic part of the thermal conductivity given by kappa E, and the phonons, that is the lattice vibration, and given by kappa L. Now, coming to the lattice thermal conductivity. So, lattice thermal conductivity in its is given by 1 by 3 C, which is the specific heat at constant volume. L is the mean free path of phonons, and v is the velocity of the phonons in the given medium. So it is directly proportional to the mean free path and the average velocity of phonons and the specific heat. And L is a mean free path that is determined by the phonon scattering on the phonon impurity scattering. So as you know, phonon is the quanta of heat transfer in the lattice. Lattice vibrational energy quanta is the phonon. And phonon can, in a given material, in a solid material, phonon can get scattered from by another phonon, or if there is any imperfections in the lattices, there some impurities or doping are there in your given lattice, so the phonons get scattered. So L is the mean free path, and it is determined by the all these things. So if you want to have a high K, so the mean free path should be more. But in our case, we want a low K, no, low thermal conductivity material. So the mean free path has to be less. So, so we have to make a material, or we have to tailor a given material or engineer a given material so that the mean free path of the phonon is is decreased, and it can be done by like impurities, adding impurities or dislocations. That is one part. Now coming to the electronic part of the thermal conductivity. So electronic thermal conductivity is now given by this term Ne mu Lt, where L is the Lorentz factor, which is for the free electrons. It is given by this term, and it changes for electrons in a single parabolic band or a multi-parabolic band semiconductor. So if you remember, on the first day we have seen like we have this EK, so it can be 1, we have this EF, and this is the K space. This is the energy, and this is the K space. And this point is the Fermi energy. This is the EK diagram. So it can be single parabola, or a material can be multiple parabola. So the L, Lorentz factor, is depending on the single parabola or multiple parabola of the semiconductor. And it is to be determined carefully for different materials. And high temperature due to excitations of electrons, so Ke become large. So Ke is generally large and it can be extracted. So we cannot exactly control the Ke at high temperature because it becomes large. So we have to see how to control the lattice thermal conductivity and the electronic thermal conductivity, so that the total thermal conductivity of the material is less. So keeping this into our mind, we have to see that the ZT is now, we have to decrease the thermal conductivity, the denominator term, and we have to increase the power factor. So this is called the power factor. So how to increase it? Now to increase the power factor, we have to optimize the carrier concentration. So we have to have a high carrier concentration material. So we can use a heavily doped semiconductor. And we have to have high charge carrier mobility. So we should have a low band gap material. So we should have a low band gap, and we should have a highly doped semiconductor. But we should not have a metal. So my first question is, today's question is, why we cannot use a metal as a thermoelectric material. So we have already discussed that part. Now we cannot use copper, we cannot use aluminium, or we cannot use gold as a thermoelectric material. So why it is so? So it is because of the factors which is already there on your screen. You can use it. So you are getting my question, everyone? Why we cannot use any metal as a thermoelectric material? Okay. Now coming to the thermal conductivity part. So we have got electrons and holes, and we have got phonons. Now if you see this graph uh, on your right. So here we are having this carrier concentration, and we are having we have plotted the ZT and this thermal conductivity and the Seebeck coefficient. So starting with the Seebeck coefficient, we see that Seebeck coefficient, as we go from insulator to semiconductor to metal, the Seebeck coefficient starts decreasing. This is the Seebeck coefficient. So it is decreasing as we go from insulator to metal. And if we see the electrical conductivity, it keeps on increasing. So the insulators have the minimum electrical conductivities and the metals have got the maximum electrical conductivity. So if we take the numerator term of our ZT, sigma S square, so this kind of parabola we are getting. So semiconductors have the maxima. Now coming to the thermal conductivity part. So if this is the lattice thermal conductivity and this is the electronic thermal conductivity. So it keeps on changing. So for insulator, the maximum thermal conductivity is because of the lattice, and in metals the electronic part is also playing a part. And then we come to the ZT. So we see that ZT is maximum, ZT max is for any given material with a charge concentration of around 10 to the power 19. So that is a heavily doped semiconductor. And how we can increase the power factor? What are the different ways to increase the power factor of some thermoelectric material? So we can increase it by doping or by densification or by crystallinity. So we can make the material dope. We can dope to make it so we can have a highly doped semiconductor. We can increase the doping and we can also decrease the band gap. If we now densify a material, we have got a material, if it is in the powder form or it is like ceramic is there. So if your density is increased, so what happens? First is electrical conductivity will increase and thermal conductivity, if it is, they are made of discrete grains. It is not a single crystal material, it is discrete grains. So obviously the thermal conductivity will be less. So that is the reason why we are not using single crystals here. Rather than we will be using polycrystalline materials as a thermoelectric devices. The other types of things which are done to increase the power factor is like point defects. We are introducing point defects like to scatter to decrease the thermal conductivity, and we are optimizing the majority carrier concentration so that the power factor increases. So this was done initially in the first generation thermoelectric material to achieve a ZT of around 1. Now in the next run, in the second generation, what people started using nanostructuring, like nano powders were used and then they were densified. Why nanostructure? Because they will be decreasing the thermal conductivity, because there will be nano grains and then we are densifying them together. So because of the grain boundaries, in the nanostructure, the grain boundaries will be playing a very big role, and on the grain boundary, what happens? The phonons start scattering. Also, you will be losing the electrical conductivity, but this is mainly to decrease the thermal conductivity. So the second generation thermoelectric materials were achieved using this with a ZT of 1.3 to 1.7. Now, third generation materials people are working on to increase the ZT to like 1.8 and more. Like we said, for commercialization, it should be around 2. So what people are doing, they are introducing mesoscale structuring, like some laser structuring is happening using lasers or different things. So at the mesoscale, not the nanoscale, but at the microstructures of the material are changing. Doping induced electronic structure modification so that the band gap is decreasing. and matrix precipitation band alignment. So this is a very detailed theory is there, like how the bands are aligned, or this parabolas which we were talking about, the EK diagram. So how they can be aligned so that the the thermal conductivity decrease without changing the power factor. So these are like a few ways, to experimentally people are doing a few of the ways to increase the power factor and decrease the thermal conductivity to get a better ZT. Now, a convention of good thermoelectric material. What is a good thermoelectric material?
Ma'am,
Yes.
yeah, I have a question. You stated that metals are not thermoelectric materials, good thermoelectric materials.
Yeah, that is my question for today's assignment. Yes.
That is your question. And
Hmm.
semiconductors can make for good candidates depending on how they are made.
Yes.
But like what I had studied in the masters and all, there are the topological insulators as well, the 2D topological insulators that are insulating in the bulk and conducting along the edges on the surface, that is. So,
Yes.
if we use such a material, we can suppress the thermal conductivity because it's a bulk phenomena and
Yeah, actually, like bismuth telluride, bismuth selenide, these are topological insulators. And in the third generation, people are using these materials as a thermoelectric. So topological insulators are not metals, as you have exactly pointed out. So they are coming into the category of heavily doped semiconductors, somewhere in that line. So as you said that they are bulk, they are conductors, but the surfaces are, so they are being used. You are correct in that. People are using bismuth telluride is one of the I will be coming to that. You can see bismuth telluride, which is a topological insulator, is nowadays used for thermoelectric generation.
okay, ma'am, thank you.
Any other question for anyone else? So I go ahead. So now few of the for last like 50 years or so, people are working on this thermoelectric. So some like keywords they have defined now, key what can be a good thermoelectric material. So optimized charge carrier density of like 10 to the power 19 per cc, per centimeter cube, like a heavily doped semiconductor. So it is in this range we can get to maximize the power factor. So that is one rule. The second rule is like the band gap should be equivalent to 10 kBT operation. So this has come from experience, where T op is the operating temperature. So small band gaps are generally good for thermoelectric performances as they lead to high carrier mobility. However, if the band gap is too small, so we can say that low band gap materials are good, but it is not so. If the band gap is too small, then the thermal excitation of the minority carrier will adversely affect, because the electrons and holes also carry heat in the opposite direction. So generally, it's a rule of thumb, you can say that we should have a band gap of 10 times kBT. Then electronegativity difference is a measure of the covalence of the bonding in the material. So like we have got large electronegative difference. Large electronegative difference indicate an ionic bond. So large charge transfer and strong scattering of electron by optical phonon. So these large scattering cause low carrier mobility. Therefore, a good thermoelectric material are composed of elements having small electronegativity difference. So like I was telling about Bi2Se bismuth selenide. It is composed of two materials. So the electronegativity of these two materials should be minimum. So that kind of materials are being used. So I will be not using a very different electronegativity like say NaCl. This kind of materials are generally not used, but this kind of material. So just an example, but yes, bismuth selenide is the third generation, one of the most studied material for thermoelectrics. Now come to average, large average mass. So we'll have, so we said that M star should be as large as possible. So a heavy atom corresponds to low thermal conductivity due to small acoustic photon generated. So that's why heavy average mass should be used. Then crystal structure with many atoms. If like bismuth cyanide is just two, but if we are making a semiconductor or like that with many atoms, so they tend to have low lattice thermal conductivity, and number of defects per unit cell tends to grow as the size of the cell increase. So we tend to have those materials which will have big unit cell, so that there is less thermal conductivity, and crystal structure that have highly coordinated ions tends to have lower thermal conductivity. This is an empirical relation. Now these are few of the elements. This is the p type and this is the n type. These are few of the materials which are used. So you can see bismuth telluride performs the best in 0 to 200 degrees. So this is the temperature, operating temperature, in both cases. So if you see that working around 200 degree, here also here. So we see bismuth telluride, which is one of your topological insulator, it is also there. So this has got very good ZT. So this there is another challenge. Now you can see that we should have a P type and its counterpart N type. Both type of semiconductors or materials you want, which will be operating in that temperature gap. Both you need, because just one p type, if you are getting a p type and you don't have its counter n type, then also you cannot take out the electricity. So we need a p type material, a thermoelectric material, we need a n type thermoelectric material to make the full module. So bismuth telluride is one which is performing very good at low temperature, and lot of work is going on in that. And if you go to very high temperature, silicon germanium, SiG, you see, beyond 800, it can be used. And in the mid temperature region, there have been many different combinations are there. So lead telluride and tags. Tags is a acronym. I will be coming to that. So this is somewhere used in the 400-500 range. So many work is going on, and we have a ZT. We are coming to a ZT of around 0.8 to 0.2 here. So these things we have to see before going into the fabrication of a thermoelectric module. Now, what are the basic steps? Now, till now we were talking about the theory of it. What is the material required? What kind of material? The material should have which kind of properties and all. But how to make the thermoelectric device? So we start with the powder of the materials, and then we make whatever like lead telluride or whatever we are making the material, and then we have to make those legs, those p type and n type. So then that is, after making the material, we have to hot press and make these legs, and then they are metallized, because you have to take the electrical from that, and also you have to connect them to each other. So they are like characterization and metallization takes place, and then we make the device. So we have got this one, each module has got one p type, one n type, one p type, one n type, and then we will be then putting all together. So it can have n number of such modules, with one p and one n, and then we take the current output. So first, so as a example, I will be giving you example with lead telluride and tellurium, silver, germanium, and antimony alloy is there. So I will be giving you the example. So then first we make the single phase of this material, and then we make metallic covers on this, shoes or covers in this, so that we can take out we can first make it coupled. The thermal coupling has to be there and electrical coupling is there, and then interconnecting the thermocouple elements into metallic strips, and then packaging, okay, and testing of the device. So starting with the material preparation. So initially the powder is taken inside a seal and vacuum sealed inside a graphite bottle and vacuum sealed in a quartz ampule at 10 to the power minus 5 millibar in the composition. And then they are put in the rocking furnace. So we are taking for the lead telluride, we are taking this material, and for tags, we are taking tellurium, germanium, silver, and antimony. These are the, so it is an alloy, okay, tags. And then they are put at 950 degree and a rocking furnace, melting plus rocking. So what is basically rocking? We have a furnace, we have a coil here. So, and we are maintaining it at 950 degree. And our material, which is this is put here. Okay, I have put it. It is in the powder form and something. Now you see, I have got tellurium, germanium, silver, and antimony. And there is some composition, no? Some say T, X, G, Y, A, G, Z, something. No? Everything will have some different composition. So the full whatever material I am making, it has to be homogeneous. So for that, this rocking furnace is there. This furnace is there. So it will be like going up and coming down continuously. So you are mixing. You are mixing. So at one given time, your material will be like this. Next time it will be like this, and next time it will be like this. Continuously, this kind of rocking is keep on happening so that proper mixing happens. So in the molten state at 950 degree there will be rocking for 2.5 hours, so that when we take it out we get this is the lead telluride, it looks like this, and the tags look like this. And then we again grind this material to make a fine powder. So you get that first is making a single phase material. So starting is that. Now we have to make the thermo element. So our powder is there now. We have got the single phase material and we have powdered it. Now we put it into these holes. Put the material, and this is the N type and this is the P type. So this is the lead telluride. This is actually thermoelectric. Our element is there. But because we have to now electrically and thermally couple them, so how to couple them? So we cannot just put directly like silver pads. We have to match them. We have to match the thermal expansion coefficient of also of this, because if you are making it into a device and if the thermal expansion coefficient of this ion material and say silver does not match. So if you see here the linear thermal coefficient, no, for our for the iron is 12 into 10 to the power 6. Lead telluride is 29 into 10 to the power minus 6. Sorry. Tags is 14 and tin telluride is 13. So we are matching it. We are not directly putting the silver pads on it. We are putting a layer of iron and lead telluride and iron on the lead telluride. And in case of the tags, we are keeping a layer of tin telluride, then iron, and then silver, so that there is a proper matching in the thermal expansion, so that the legs, our the thermoelectric elements, the modules do not break, or this junction, no, this junction or this junction should not come out when we are operating it at a temperature like, no, our we have a hot junction. So this will be say at 500 degrees centigrade. I have a cold junction. This will be at my 25 degrees centigrade. And there will be this of my lead telluride. So this is my lead telluride. So you can see the kind of thermal shock this is undergoing at a given time. So there can be this junction can come out. So we have to see that it is formed properly. So we are using silver disc, we are using graphite disc, graphite liner around this, and then we are also putting the iron and iron lead telluride and tin telluride. So we put all this material in this, and then we are putting the lid, and now we are vacuum hot pressing. What we do in vacuum hot pressing, the base vacuum is transfer -6 star. Temperature we are going to 1200 degree. We are going temperature above the melting point, the formation point of our material. And then we are also putting a load of 40 ton, so that our silver legs and all, it is forming a junction. And this is how it looks like. Now this is our full thermoelectric, one junction, one leg and the other leg. So, and this is just like 15 mm diameter. 15 mm diameter is like 1.5 centimeter. So different are made. So here you can see even small size are also made. So now this has got our silver on top. Then there is the diffusion intermediate layer and our actual material. So this we have made, and now we are now fabricating the device. So our PBT and tags. So this will be at one temperature T1, this will be at T2, and they are electrically in parallel, in series. So current will be flowing like this, and it will go to the next. So here this is one module. Here we can get two modules. We can see which are connected. So the voltage is taken out from here. So current will be flowing like this. Now it will be going to the other one, this way, and it will be coming out. So thermoelectric modules are in temperature, they are parallel to each other, but electrically they are connected in series. And the contacts are taken using silver paste or brazing alloys. But this leads to, though you can see that we have made a device, but it is not so. These devices are very unstable. And this contact resistance, because you are taking out voltage, so the contact resistance at each point should be very less. But generally we get very high contact resistance. And cutting into small pieces like this leads to the breaking of pellets from the interface. So when making the devices, we have to take care for all these things. Now we were seeing only just like four elements were there, now two P type and two N type. But then if you want to have a very uh, uh, high output, so we should have many elements. So if you want to have many elements, so you should have a asbestos sheet or a silica composite sheet on which you will be putting your elements. So these are the elements, and this thermal conductivity is there, and then we are putting it into the asbestos sheet. So each element we can put it here and then connect them. So now here you can see that this is the jig, and silver foils are kept on them, so that two gets connected on this side, then the other two on the other side. So two like this, two are connected. These two, these two, and rest are connected. And then they are put on this mounting plate and ready for vacuum hot press. And again they are hot pressed so that we can make the final device. And this is how the final device look like. So this is the contact resistance, and this is the final device you can see. And here they are, here this is the heater at 500 degrees centigrade, and this is the cold end, which is at room temperature or water cooled. You can see water flowing, and some 0.3 millivolt is generated. So you can see that the full thermoelectric generator device we could make, starting from the raw material, making the raw material into a single phase, then making the P type and the N type, taking electrical contact, then joining different modules, and then making the device. So this is how a thermoelectric generator device is made and then uh, used for different applications. So let me know if you have got any questions. So let us have a question answer schedule and then we will wind up. So any questions?
Not from this.
No questions from anyone?
No, ma'am.
No, ma'am.
Can
Okay.
you repeat the assignment question once again?
What you are asking?
Can you repeat the assignment question once again, ma'am?
Okay, you were not there. Okay. The question was why we cannot use any metal as a thermoelectric element. Why a metal is not a good thermoelectric material? That is the question for today. That is the only one question for today. So before taking leave, I will say that till now we had completed semiconductor, basics of semiconductor. Then we completed a single crystal growth. Then we completed thin films. And now today we have completed the thermoelectric devices. So I have only one lecture now remaining, and there we will be covering the photovoltaics. And my next lecture will be in the new year, 2026. That is on 2nd of January. And I wish all of you a very happy times and have a nice vacation. And see you then. And just answer the question. Very small question is there today. And let me know if you have any doubt or anything. Okay. So thank you. Goodbye.
Ma'am,
Ma'am,
Yes, yes, yes. Yeah, one by one you can talk.
will you be covering the piezoelectrics as well?
No, no, that is not in my piezoelectricity is not there.
Okay.
Some other
ma'am,
question?
material is not uploaded yet on that sheet.
What? What is not uploaded?
Material, that PPT material is not uploaded yet.
Okay, I will see to it. I will
Okay.
see. Sure. Anything else from anyone? No question? Okay. Okay, have a nice time. Bye.
Same to you, ma'am. Same to you.